Today we're going to be looking at half-lives and what they are, how to solve half-life problems, and also how to graph the data that we get from half-life problems. So what a half-life is. A half-life is simply the amount of time it takes for half of a radioactive substance to decay into a more stable substance. In this diagram here, you can see this represented by the parent isotopes and the daughter isotopes. At 0 half-lives, so at our original start time, we have all of this parent radioactive isotope. And then after 1 half-life, we now have half of our original sample from before. And the other half has turned into the daughter product. So it doesn't just disappear, but rather it turns into something different. After another half-life passes, then we lost half of our previous original sample again, and it turns into the daughter product. If we look at this in a graphical format, you can see in this graph over here, we have that represented where you got all these parent radioactive atoms, and then half of them decayed after 1 half-life. The next half decayed, another half, and so on and so forth. This graph I really like because this one shows our percentage of original isotope. And when we look at the percentage, we see a nice curve here. And what kind of decay this is actually called exponential decay. And exponential decay is different than linear decay. Linear decay would be a line that's just kind of going straight down the graph. But with exponential decay, you have a fast decline and then it gradually tapers out. So you have more of that curve to the graph. If we look at this graph here, this is showing the radioactive isotope of the decay of the parent isotope, but then it's also showing on the same graph the isotope percentage of the daughter isotope. So the new isotope that the parent decays into. So you can see on this one we have the exponential decay, but now in the daughter isotope we also have an exponential increase. And these two are going opposite of each other, and that's actually called an inverse. So these two are inversely proportionate to each other. As the one is going down, the other one is equally going up. Okay? So as we look at these half-lives, let's actually plug in some numbers here to see once what that looks like. Here would be a data table showing the grams of sodium-24 and the hours that would have passed. Now you can see up here that the half-life of sodium-24 is 15 hours. So I'm going to say half-life, that's how we denote that. I'll just say 15 hours. So at time 0, I started with 100 grams of sodium-24. After 15 hours passed, which would be 1 half-life, I can see here that my amount of the substance cut in half. Now after another half-life passed, how many grams would I have here? Well, it would be half of my new original amount. So half of 50 would be 25. Here I got another halved amount. So another half-life would have passed. So another 15 hours. Here, same thing. Another 15 hours is going to pass. And on this last one, one last half-life passed over here from 60 hours to 75 hours. So then my amount over here would be approximately 1.25. Okay. Now if we're actually given a problem of a certain substance, we're going to be given something that has the starting amount, what its half-life is, and we want to figure out how much we might have after so much time has passed. So in this problem it says the half-life of radium is 11 days. I'm going to just kind of write that over here so I remember that. I also underlined it in the problem to help me with it. It says if you start with 240 gram sample of radium, how much will be left after 44 days? And then we're also going to look at the percent left. Now there is a logarithm type equation in order to solve for this exactly, but we're going to just break it down and think through the concept instead for right now. So if I started with 240 grams, I know that, and I know that I'm looking at how much is left after 44 days. Well, in 44 days, I got to figure out how many half-lives that is. So I'm going to do a little dimensional analysis here. So I know that 11 days equals 1 half-life. So I can cross out my units of days and days, top and bottom, and I would be left here with 4 half-lives. A lot of times we'll just think divide 11 into 44 and we would get our 4, which is true, okay? But this is how we're getting our new units. So I need to have 4 half-lives that pass. If I start with 240, half of 240 is 120. That's going to be 1 half-life. A second half-life, half of 120 is 60. That's 2 half-lives. Third half-life, half of 60 is 30. Then my fourth one is 15 grams. So how much will be left after 14 days? That'll be 15 grams. Now, in order to find the percent that's left, there's 2 different things I could do. I could take 15 grams, divide it into 240 grams to get my overall percentage. That's my percent of my original. Or I could do the same kind of breakdown here, but using the percents instead. So when I started with 240 grams, I started with 100% of the sample. So I'm going to write 100%. That gets cut in half to 50%. That gets cut again into 25%. And I keep on working my way down. I can even draw the brackets in here if I want to check my work. 1, 2, 3, 4 half-lives. And I am left with 6.25%. Either way will get you the same answer. Now if you take the same problem, and here it's asking to graph the results. Go ahead and pause the video and see if you can graph the results that you just found. And hopefully this is what you came up with. Now you can see that I have 2 different graphs. This one I put half-lives on the x-axis, and this one I put days on the x-axis. But I have grams on the y, and you can see the exponential decay in both. The main thing to keep in mind is that you have even units as you go up. Don't start skipping units. Make sure you keep even units all the way. All right, we're going to move on to another half-life problem for radium-255. And if you think you know how to do these already, go ahead and pause the video right here, do the work, and then you can check your answer. If you need another guided practice, then keep the video playing and we'll go through this one together. So for this particular one, it's saying the half-life of radium-255 is 15 days. Approximately what percentage of radium is left after 90 days? So my half-life is 15 days. And I'm not given a starting amount. I'm just asked for what percentage will be left after 90 days. So I need to figure out how many half-lives I'm dealing with. So 90 days and 15 days will go on the bottom, which that equals 1 half-life. Units cross out, units cross out. Okay, so that's going to be 1, 2, 3, 4, 5, 6 half-lives. So now if I start with my 100%, because you're always going to start with 100% of a sample, and I keep breaking it down, having my 100%, it's going to be 1 half-life, 2 half-lives, 3 half-lives, 4, 5, and I need one more for my 6 half-life, and that's going to be approximately 1.56. We'll just kind of round there. So the answer to this would be approximately 1.56% will be left after the 90 days. So if you're just joining us back, check your answer, see if your work and your answer matches up. Now, one concept that we have with half-lives is carbon dating. And carbon dating is specifically talking about the carbon-14 isotope. Now, as you can see down here, we have 3 different isotopes of carbon. Carbon-12 is going to be the most common type of carbon. 98.89% of all carbon that exists is in that isotope. Carbon-13 has a very small percent, and carbon-14 has an even less percent that is in existence. But as you can see over here in this diagram, carbon-14 that does exist is going to be able to get into all different living organisms because it's in the air. So producers such as trees or grass are using it, taking it in as part of photosynthesis. So the carbon-14 becomes part of their plant matter. If anything eats the plant or would eat something that eats a plant, then the carbon-14 also gets passed into those people or animals and is in their tissue. So when the tree dies or when the animal dies, this carbon-14 is in the bones or is in the material that once made up that living thing. Now, with carbon-14, it has a large half-life. Carbon-14 has a half-life of 5,730 years. So with carbon dating, what that is using is this carbon-14 isotope and trying to age different things that are found. So initially, when that living thing died, it had 100% of the amount of carbon-14 in it. So that would be age 0. But after 5,730 years, you have approximately 50% of that isotope. And that just continues to go. And so that is one way that we can use half-lives in order to help date things that we find. Another use for half-lives is within the medical field. You'll have that with different iodines or things that can be used in order to diagnose things. And then we have to just be aware of the half-life that those radioisotopes have, because you don't want that to be in a person too long. Now, here is one last half-life problem to try, and this one is using the isotope of carbon-14. It doesn't change anything with how we solve it. We're just using a little bit bigger number with our half-life amount. So why doesn't everyone go ahead and pause the video, give this one a try on your own, and then check your answer once you're all done. Here would be the work and the answer for that last problem. So hopefully yours matches up, and hopefully this video was helpful for you.